All right, there we go.
Mhm.
So I thought this would be the last day where we had physics CM questions, then we'd start doing physics A stuff, but it turns out 2019 had two sets.
Mhm.
So we'll still be doing physics C for Wednesday,
Okay.
but we're almost done. So we're looking at the third question for physics C in the sheet that's pushed out through WeChat.
Mhm.
Um, we'll be looking at rotational inertia and determining angular velocity given a set of equations.
Okay.
Okay, you got a pen? And okay, so what's happening here is we've got two disks. So this lower disk is vertically oriented, and this upper platform is being spun by it. So as the motor spins around and around and around, that drives the platform around and around and around along its vertical axis. Okay, any questions on what's happening with the picture?
No.
Okay, so we're told we've got rotational inertia, I, for the platform. And we are making contact with the motor-driven wheel. The wheel has a radius r and touches the platform a distance d from the vertical axis. So radius r, distance d. The platform starts at rest, and the wheel exerts a constant horizontal force of magnitude f, tangent to the wheel, until the platform reaches an angular speed of the angular velocity of the platform after time change in t. During time delta t, the wheel stays in contact with the platform without slipping. I want to derive an expression for the angular speed omega p of the platform and express our answer in terms of the rotational inertia of the platform, the radius r of the motor-driven wheel, the distance from the motor-driven wheel to the vertical axis, the force that we are applying from the platform on the wheel, and the change in t in physical constants. What do I need to do?
So torque is equal to I alpha.
Okay, and that's the rotational inertia of the platform in our case.
Yeah, and uh that's also equal to force times radius.
I need to be more specific here because I've got two different,
Oh, okay.
really three
So
different radii.
force times d.
Right. So that's my distance from the axis of rotation to where we're going. So in our case, uppercase d. So that's is the rotational inertia of the platform times alpha. Okay. I need to. Our goal is to solve for omega. So let's solve for alpha, and then we'll change it to omega.
So alpha is equal to omega over t.
Okay. Let's solve for alpha first, then I'll change it back.
Oh, okay. So fd over inertia.
Okay. Then we need to use some sort of an equation in order to change alpha to omega.
Yep. So omega p over delta t is alpha. And also equal to fd over um I fd over I, yeah. So omega p is equal to fd t over I.
Okay.
Yeah.
So this works in this case, because we were starting at rest. If we weren't starting at rest, this actually wouldn't have worked. And the reason why is because this equation is getting an average.
Oh. Yeah.
However, in this case, we could say that our angular velocity right now is equal to our initial angular velocity plus a dt with our kinematics equation. We end up getting alpha is wp over dt because our initial velocity is 0.
Yep.
Okay. Part B. Expression for kinematic energy, the moment it reaches wp, or omega p, in terms of our rotational inertia of the platform, radius of the motor-driven wheel, distance from the vertical axis to the driven wheel, force applied between the platform and the motor, and our change in time or any physical constants.
So, kinetic energy for this one is half I omega square.
Okay, and that's the angular velocity of the platform in our case, and the rotational inertia of the platform. And we said back here that we've got an equation we could use to solve for that. So our WP we can substitute in is FD dt over IP.
Yeah.
Okay, so if we simplify, what's going to happen to our kinetic energy?
Inertia times 4 squared distance square t square over and inertia 2 inertia square. So one inertia cancels out.
Okay, that's good. Then we also need to derive an expression for the angular speed. Of the motor-driven wheel at that time.
So motor-driven wheel is V over R.
I think you're saying this, the angular velocity is v over r?
Yeah, but I don't know how to... Wait, Do we use conservation of angular momentum?
I don't think we need to.
Derive.
If the platform started at rest, what was happening to the motor-driven wheel?
Also rest.
Also at rest. If the linear velocity of the platform at that contact point has to be the same as the linear velocity of the motor-driven wheel. Right? Okay, then I'm going to start there. So that's VW must equal VP. But now I need an equation for VP and an equation for VW.
Okay, so VP was omega P over R. Oh yeah, omega R.
Okay, what's RP? For
RP is R.
RP is not R. So you said R is the radius of the motor-driven wheel.
Oh, D.
D. Okay.
Oh, and then VW is omega. Is it omega W? Yeah, omega W and R.
Equals omega PD. Okay.
So we already know omega P.
We do. I think we can just go from here actually. So solve for
Okay.
omega W because that's in terms of D, W, P, and R, and we've already got
Oh,
that. So we should be able to
yeah.
just solve from here.
Omega P D over R.
Yep. Which I think is okay because they told us to express our answer in terms of that, so we should be all right.
Mm-hmm.
Okay, last one, D. So this time, the motor-driven wheel is going to be removed while the platform is spinning. The student holds the disc directly above and concentric with the platform. So we have a second disc that's being held above the platform like this. The disc has some rotational inertia, IP, which is the same as the platform. And then they're going to release the disc from rest. It will fall onto the platform, and after a short time, they're going to be rotating together at the angular speed, final angular speed.
Oh, okay.
Okay, what's going to happen?
So we use conservation of momentum.
Okay, L1 equals L2, which in terms of rotational momentum, angular momentum, what's our formula for angular momentum?
It's I omega.
Okay, so I've got I1 W1 is I2 W2. So that's our angular, our inertia of the platform times our angular velocity will equal the inertia of the platform again, since we know that that was the same, times the angular velocity of the final disk. But we're going to have double that inertia because we'll have both disks together at the
Yeah.
end. Okay, I'm going to rewrite this. 2IP. Okay. So initially we just have one disk spinning, now we've got two disks spinning, so we'll have double that inertia.
Mm-hmm.
And then we solve for WF.
IP the omega P over 2 IP.
I think the IPs are going to cancel.
Yeah.
Okay, so this is just omega P over 2.
Yeah.
Okay. Let's see, what's our timer at? Okay, I'm at the 15-minute mark. I am in break here. That's not the end of the problem, though. However, E, F, and G is based on a best fit graph.
Mm-hmm.
And I don't really have a good way of doing that from here. I want you to do the best fitting graphs on your own because we've had trouble with those in the past. When you go to draw your best fit line, try to make sure you've got the same number of points above it as you do below it, okay?
Mm-hmm.
All right. So I'm going to stop here, and you've got question 1, 2, and the rest of 3. So that's E, the graph, and then F, G, 2 questions about the graph. To finish for homework, okay?
Okay.
All All right. Thank you so much for coming. And I will see you tomorrow for Calc 2.
Bye bye.
Goodbye.